On to our main speaker, David Hughes. We're delighted to have him. He's come over especially from Sheffield. This man is a comet expert. Now, there are very few of those around. Okay? So much so that a comet has actually been named David Hughes. In this year of International Year of Astronomy, we're celebrating Galileo not necessarily inventing the telescope, but looking through it. We're at a junction in our own physics courses where astronomy will be hopefully introduced. Okay? And today there's a sort of miniature theme of astronomy running through it. We have later on the workshop from Rob Hill. Okay, so without me, you don't want to hear me talk anymore. I want to hand over to David. Please give him a nice warm welcome. Thank you.
Well, thank you very much indeed. I have really enjoyed coming here to Ireland. It's not my first time, but a lovely spot. I'm going to chat to you today about telescopes, how they were produced, and how they're being used, and how we are all, we being the taxpayers, paying lots and lots of money for big telescopes. And you've already heard that 2009 is the International Year of Astronomy, and in 1609 Galileo used the telescope astronomically for the first time. You quite often read about Thomas Harriot in England supposedly inventing the telescope. Forget it. I mean, Thomas Harriot, bless him, he was a mathematician, he had a cushy job, he worked for the Earl of Northumberland, and he looked through a telescope, he drew a little picture of the moon and then forgot it. He didn't publish his results. Whereas Galileo was a proper scientist. And here you have a man who wanted a telescope, so very fortunately he was in the right place. He was in Florence, where people were very good with lenses, and he got his technician and himself to make a telescope. Not only did he use it, he observed the moon, he observed Venus, he observed the sun, he observed Jupiter, he wrote up his results, he published his results, he sold his publication, all before the end of March 1610. Now, before I really get going about telescopes, let me just say that the introduction of the telescope to science was a seriously major event. This date, 1609, was an absolute watershed. Before that date, humans, us, scientifically, could only use the five senses. And so, if we couldn't smell it, taste it, feel it, hear it, or see it, it didn't exist. You then get, in 1609, this instrument, the telescope, which suddenly changes the ability of humans to see things. I mean, look, we all use our eyes all the time, and we know that we're stuck with a maximum pupil size of 5 millimeters. And if it doesn't go through these 5 millimeters, tough, you don't detect it. We're also stuck with a minimum resolution of 1 minute of arc. I mean, outside the hotel window last night was the quartered moon, a lovely sight in the sky. This, of course, subtends half a degree at the eye. You hold your finger up, that subtends 1.5 degrees at the eye. You can cover your moon up 3 times with your extended finger. But with the eye, all you can do is resolve a minute of arc. The moon is 30 minutes of arc across, and so before 1610, this just tells you how limited our observations were. We're also stuck with the fact that the brain-eye combination sees a picture about every 24th of a second, and then it sees another picture, and then it adds these all together. But as soon as the telescope came along, let's face it, the telescope is a marvelous piece of kit. I always say to my students, in essence, it does 3 or 4 jobs. One of the major jobs the telescope does is act as a light bucket. So if you've got a big telescope that far across, you collect up the light that hits the whole diameter of that lens or mirror. And of course, you can then funnel that light into the eye, and you can see things which are too faint for the eye to detect. And this, of course, was amazing. In 1609, Galileo, for example, looked through the telescope and realized that there weren't just the 4,000 stars that you can see in the sky, there were more. And so Galileo said, well, why did God make things that we can't see? And this philosophical discussion started going. And I shall be telling you later on that we got so keen on the telescope as a light bucket that we have been quite happily increasing the diameter of the biggest telescope on planet Earth by a factor of 2 every 50 years. And as yet, nothing has stopped us doing this. Well, of course, the other thing that a telescope acts as is a magnifying lens. This 1-minute resolution is completely knocked on the head by telescopes. And of course, with the biggest telescope on Earth and the Hubble, you can get superb stellar resolution. And as you've been wandering around outside, you've been seeing some of the pictures that have come back from Hubble. I mean, the Whirlpool galaxy, for example. You just look at that Hubble picture today, and you're seeing something which is about 18,000 pixels by about 5,000 pixels across. And you're seeing a beautiful image, which, well, let's face it, in 1773, the Whirlpool galaxy was discovered for the first time. 6 years later, they realized that it wasn't one galaxy, it was 2. And then here in Ireland, up the road in County Offaly, they actually drew these wonderful spirals that you can see in that galaxy. And this is all down to actual telescopes. And then the third thing that a telescope can do is measure position. And here again, in astronomy, the use of telescopes to measure where stars are has been very, very important. As, for example, the Earth moves around the solar system every year, within a 6-month period, the Earth moves 300 million kilometers. And of course, this makes nearby stars wobble about in the sky, but only by about a second of arc. And early telescopes couldn't detect this. And so people kept saying, well, are you sure the Earth is moving around the sun? I'm standing here, I don't feel it moving around the sun. And so Galileo used to get into these great big arguments. But as telescopes got better and better and better, we suddenly got to a stage where people could say, oh, we're just able to detect this. And so we could then do something which in astronomy is absolutely vital, and that is measure distance between us and stars, and come up with silly facts like, you know, in our neck of the galaxy, the average distance between stellar systems is 7 light years. We can look at the Whirlpool galaxy in the sky and not say, oh, isn't that fascinating? We can also simply tell you that that is 150,000 light years away. And so you suddenly realize that what you're looking at is of a certain size and has a certain number of stars. And this, needless to say, is a vital business. So, when it comes to this lecture, let me get started. And let's see if everything works. Whoops, hold on. Page down, page up, nothing's happening. Where's my technical assistance? I want to use this. No? Okay. Can I not?
Up and down.
Why is it not doing it? It doesn't matter, I can use that.
I'll just power it down. Yeah.
There we go. Here's Galileo. He started doing his good stuff when he was 45. I love that, being a grey-haired bloke. I get so cheesed off by people saying that if you haven't done it in your 20s, you'll never do it. Forget it. This man did all his science when he was 45 and 50. And if ever you want to get really interested, do read up about Galileo. He was an absolute bastard. Well, that might be a bit rude, actually. Maybe he wasn't, but certainly his two daughters and his son were bastards, because Galileo completely forgot to marry their mother. And then when he got promoted, because the mother of his children was lower class, he just dumped her and moved to another town and left her behind. So he was a bit of a sod. He used to love putting people's noses out of joint by, insisting that he could prove things. And he did prove things. This man not only built a telescope himself, but he properly used it. He looked at Venus. He realized that Venus not only had crescent phases, but also had quartered and gibbous phases. And this proves that Venus goes around the sun. He looked at Jupiter. He discovered 4 moons with his telescope. This proves that other objects in the solar system have things orbiting them other than the Earth and the Sun. And of course, being a sensible scientist, he named these 4 new moons around Jupiter after his patron, who was so tickled that he gave him more money. He looked at the Sun, and he noticed that it was spotty. Now, people have noticed that the Sun has been spotty for 2,000 years. But Galileo didn't go with the normal feeling that, oh, there's something in the way between us and it, another planet or something like this. Galileo didn't just look at the spottiness of the sun. He looked at it one day, and then the next day, and then the day after. He noticed the way the spots were apparently moving across the disk. He worked out that the sun is going round every 28 days. He published this observation. Fantastic. We astronomers still don't know why the sun's going round every 28 days. You look in any astronomy textbook for the answer, it's not there. We ignore the question. It's too difficult for us to answer. So here you have a marvellous man. He looked at the moon. I was looking at the moon through the window last night. Aristotle had insisted that the moon was perfect. It was a celestial body. It was smooth. Galileo looked, he said, oh, it's not smooth, it's got mountains on it. But he didn't stop there. He got out his maths, bit of geometry. He looked at the lengths of the shadows casted by these mountains. He worked out the height, published it 2 months later. The moon's not only got mountains, they are, some of them, 5 kilometers high. This is proper science. And it's this bloke that did it for us. Really got science going. Absolutely marvellous. This was his telescope. Now, this, needless to say, is, I am afraid, a rubbish telescope. And it's a telescope made up out of, whoops, I can't find it. Just a minute. Either I've lost, I'm wearing them. I do apologise. Let's go back to the invention of spectacles. Now again, you're physicists in any physics lab, it's knee-deep in lenses, isn't it? The first specs, I can see quite a few people wearing specs here, were introduced around about 1350. And these were typical convex lenses. Me, for example, 3 diopters, what are these ridiculous non-psi units? This means that the focal length of these things is 100 centimeters divided by 3. And in my late 40s, my arm wasn't long enough to get the paper further enough away from me able to read it. So I had to have a pair of these. Presbyopia is obviously solved by having a pair of these. But other people, younger people, were myopic. And they couldn't see distant objects. So instead of needing a convex lens, they needed a concave lens. Me again. Driving glasses, you see. Whoops, you're all a lot clearer. Now you're a bit blurred. And this meant that if you wanted a pair of glasses, you went to the local peddler who had a box full of lenses, and you squatted around and said, oh, those will do for reading, fair enough, and these will do for long distance. But eventually, somebody playing with lenses. I used to love doing this in the physics lectures, playing with lenses. Suddenly realized that if you had your reading glasses there and your long distance glasses here, you've got a telescope. Now, it worries me. I mean, the first sort of long distance glasses were introduced in the late 15th century. Why did it take until 1609, Lippershey, Denmark, Galileo, Florence, for people to invent the telescope by sticking two lenses together? I mean, I just don't know the answer, so please don't ask me the question, but we humans were a bit slow on the game. This, of course, is the Galilean telescope, and you'll see this in all the magic books. You have here your objective convex lens, here you have your eyepiece lens, here's your focal point, here's the jolly old eye, and of course you, as physics teachers, know two things about this telescope. Firstly, it gives you a proper image the right way up, so it can be used for opera glasses. But this telescope has one ridiculous problem. The field of view is awful. The field of view of Galileo's telescope was, at best, a quarter of a degree. This means, of course, if you're looking at the moon, you can only see, well, a quarter of the area through your telescope at any one time. Also, you will notice, well, you don't notice in this slide because it's not a very good one, but the eye is just stuck here. Where do you put the eye? There's no eye ring in a Galilean telescope. Ridiculous. And so, if you move your head slightly, what you're looking at just simply goes out of view. So that's not a very good scheme altogether. So this original telescope that Galileo had, here's the lens that he made himself, worked with great care, but was actually a rubbish telescope. And here we have a little diagram showing you how telescopes were probably invented in lens shops. Although I do apologize, somebody here says Lippershey discovering the lenses. This word is completely wrong. It should be a telescope that he's discovering in this situation. Now, then, a year after Galileo had really got going and published his Sidereus Nuncius in 1610, along came this lovely man, Johannes Kepler. Very, very famous astronomer. Do stop me talking. I can go on for an hour just chatting about him. You know, another of these marvelous people. I mean, his mum was tried for witchcraft. His wife was a prostitute. But in 1611, theoretically, which is typical of Kepler because he wasn't a very handy bloke, he discovered another telescope which we now use a lot. And this, of course, is the Keplerian telescope. Now here you've got an objective lens, which is typical reading glass sort of thing. And this is a convex lens. Here you have an eyepiece lens, and the focal length of the objective, focal length of the eyepiece is such that if you divide the focal length of the objective by the focal length of the eyepiece, you get the magnification. And you all do this in the physics class. Now, this instrument has a specific position for the eye to go, which is very, very useful. And this is the eye ring, which is over here, which, of course, is where the objective is focused in the eyepiece. What is also really important about this telescope in the historical context is that you can produce an image out here. So you can look at the sun, well, not look, you can in fact image the sun through this telescope and have an image of the sun at the back end here. And this is exactly what Schneider did in 1630. And then he went on to whinge on about sunspots as well, using this sort of telescope. So here you have a marvelous instrument, which, needless to say, is very, very exciting and really got telescopes going. And you then get the next step in telescope work. And here we thank our dear great English astronomer, mathematician, genius, Isaac Newton. He did so many things, but what he did do was also devise a telescope, and the Newtonian telescope is again a light bucket, but with the Newtonian telescope you have here a mirror, not a lens, to collect up the radiation that comes in from the left. And then, of course, Newton knew that these mirrors would do this, because let's face it, mirrors were fairly commonplace. I mean, the Egyptian ladies were using mirrors to look at each other. Mirrors were used as burning instruments to, in fact, light fires and so on. But, of course, what happens here is the light comes in, and then it comes to a focus here, in the tube. Well, that's no great problem if this mirror is 4 meters across, but Newton's mirror was very much smaller than that. And what Newton did, which was groundbreaking, was introduce this little flat here, which was held by 4 little bits of metal called a spider. And this simply deflected the focus point to this spot. And then you simply use the eyepiece as a magnifying glass to look at the focused image. And the eyepiece is here at the side of the telescope. And so what you get is a lovely little instrument like this, with the mirror at the bottom and the eyepiece up there at the top. Now, this has a bit of a disadvantage because, of course, when you move the telescope around to look at different things on the sky, you've got to move yourself around because you're looking through this little spot up here. And so you then have to try and get around that. And you then get a whole gang of people trying to get round that little problem. And the first person to do this was Cassegrain, who was a professor of physics at Chartres. And he decided that instead of having a flat mirror here and getting the image out the side, you would have a secondary parabolic, and you'd drill a hole in your primary mirror, and you would bring a focus here at the back end, which of course is ridiculously useful, because let's face it, when we start moving on in this lecture to what we're doing with telescopes, taking pictures, producing spectra, photometrically measuring brightness as a function of time and so on, we need to tie a decent instrument to the back end, and sticking it here behind the main mirror is engineeringly much better than having it hanging around up at the top end. And even then, having that focal point at the back is a bit complicated. Here, for example, you have a perfect example of a mirror, a telescope that I hope you've all got lurking around in your schools. You go and Questar makes these. Everybody makes these lovely little telescopes nowadays. You have a big mirror at the back, you have a corrector lens, you have a secondary, a focal point down the bottom end here. This is a Schmidt-Cassegrain. Well, it's a Baker-Schmidt-Cassegrain. I don't want to go into all the detail, but Schmidt invented a telescope like this with a corrector lens and a mirror. And of course, the reason this is such a superb instrument is because it's compact and also has a large field of view, which is flat-ish. And so you're then doing really what you want in telescopes, improving magnitude, light gathering power, and magnification. Whoops. The other great breakthrough in telescope design was it wasn't by anybody at all, sorry, it's called the Coudet. I made a ridiculous mistake once. I knew who Cassegrain was, and I kept reading in books about this French Coudet, and I got in touch with a friend of mine at the Observatory in Paris and said, "Who was Coudet?" And she said, "It means elbow, David. There is no Coudet. It should be a sort of a small letter to start off with." I mean, you can just see, I hope, as physicists, what the advantage is using one of these telescopes. You've got your primary, you've got your secondary, you've got your tertiary, and of course you're bringing the light from outside down to here as the light bucket. You're then reflecting it back, and then all the light is coming to a focus there at that spot, independent of where the telescope is pointing. Absolutely independent of the telescope pointing position. And so if you want to build a spectrometer that is the size of this room, and I've seen them all vacuumed and so on, you don't have to have this flung around the sky on the back end of a telescope. You can have that thing lurking down here at one specific spot. And so you finish up with an observatory with a telescope in it that looks a bit like this. You have your instrument here upstairs, and I'll explain why it's upstairs in a minute or two. And you have your main mirror, you have your secondary, you have your tertiary, you have your focal point. And then you can build your spectrometer in these 3 rooms here, and everything works beautifully. And so you're beginning to see in this picture the sort of thing you get in a modern, decent telescope. But let's go back a bit to the development of telescopes in history. I've already explained to you that the magnification that you get with a simple refractor telescope, a telescope that uses 2 lenses, is equal to the focal length of the objective divided by the focal length of the eyepiece. And what we do need in telescopic work is magnification. I mean, people love magnification. You see one mountain on the moon, you want to see more. You see a few craters on the moon, you want to see tens of thousands of craters on the moon. You look at Mars, you want to be able to see the canals. Well, of course, they don't exist, but you see channels on Mars, and you see that one hemisphere is different to the other. You look at Jupiter, you immediately notice a lovely planet in the sky. People were watching Jupiter last night. You've all been seeing Jupiter in the south in the late evening for the last month or so. So you look at Jupiter with the naked eye, you see the brightest object in the sky. You use the binoculars, you discover the 4 moons. You use a small telescope, you say, hello, Jupiter's got a spot on it, a red spot. And instead of just looking at it for a minute and then going in for a cup of coffee, you look at it for a minute, and then you come out and look at it again, and you look at it again. And being physicists, you soon discover that Jupiter's going round every 9 hours. The sun's going round every 25 days. Why is there that difference? Again, please don't ask me, because I don't know the answer. I know why Jupiter's going round every 9 hours. I don't know why the sun's going round every 25 days. But this is the way telescopes advance. And this is the sort of telescope that dear old, down the bottom end here, Hevelius was using. Lovely astronomer. Here we are in the 1650s. Hevelius was a brewer and got cheesed off with making all the money by brewing beer. He spent the money, for a start, buying 3 houses and sticking his telescope on the 3 houses. This is his telescope. Objective lens is up there, eyepiece lens is there. This is 45 feet long. I apologize for using 45, but 45 feet is the distance between that door there and this door here. Imagine on a nice windy Irish night looking at this, wobbling about. Fair enough, it takes time, but he being Hevelius down here, seriously produced a superb map of the moon using this instrument. When we move on, one of the great problems of early telescopes was the aberrations. Terrible problem. You use lenses, you're stuck with chromatic aberration. The different colors of the rainbow are brought to different focal points. That telescope you see here that I showed you using, that Hevelius was using, the difference between the focal position of the blue light and the focal position of the red light was that much. What this means is, of course, that your image was never in focus. Your image was always colored and chromatically messed about with. You also have spherical aberration. You also have coma, all these problems. This bloke, Dolland, came up with a very bright idea. He decided that if you had 2 lenses stuck together, one made out of crown glass, one made out of flint glass, these being cemented using Canada balsam, you would then be able to bring at least the blue and the red to the same focal position, even though you couldn't manage the middle of the spectrum to that position as well. And so with an achromatic doublet, you get this single focal point for your blue and your red, even though, unfortunately, the yellow focal point is still here, which means that if you've bought a pair of reasonably priced binoculars and you're bird watching, you look at a duck on a pond, that duck has got a yellow halo around it. What can you do about it? Simple. You spend another £1,000 and buy some Zeiss binoculars, which don't have a doublet at the front end, but have a triplet, which, quote, solves the problem. And of course, being as these lenses are fairly big, I'm not going into the horrible thing that whenever, for example, you pass light through a lens, some of it gets absorbed. If you've got loads of light to start off with, wow, who cares losing the odd 10% on the way down? And likewise with mirrors. Whenever light is reflected from a mirror, you lose some in absorption. So if you have a telescope with 3 mirrors in it, you're losing light at the first, and at the second, and at the third. But, you know, you've built a big telescope, so what the heck, there you go. Dolland invented this achromatic lens, which seriously solved one of the problems. So much so that with a good Dolland lens at the top end of this telescope, in 1835, this bloke actually measured the wobble of the star 61 Cygni on the sky as the Earth moved from one end of its orbit to the other. And this chap here immediately rushed out and said, this star, the 61st star in the constellation of Cygni, is not just out there. This star is actually 2.3 light years out there. So then, of course, you, knowing the star's brightness and its distance, can measure its energy output, and you can compare that to the energy output from the sun. This bloke not only noticed 61 Cygni wobbling about, he also noticed Sirius and Procyon wobbling about. Sirius, for example, is Alpha Canis Majoris. Being a proper scientist, he said, why is that star wobbling about? It must be gravitationally being influenced by something else which I can't see. And eventually we did see what was doing it, and this was a white dwarf star, a completely different type of star. Something we could have never have discovered with the naked eye. Something we wouldn't have even thought of with the human brain. A star with the mass of the sun shoved into the volume of the Earth. I mean, you've all come across these density calculations. You know, a max box of a white dwarf weighs as much as a steam locomotive, all this sort of stuff. All down to this bloke here and his telescopes. Whoops, sorry, wrong button. This is it. Lovely, lovely instrument. And you can see what's happening. You have the best optics, and you've got the engineers on the job, producing the best physical mounting. And it's the combination of these two that enable the scientist to make the breakthrough. Now, before I go on, let me talk about another little topic. Where do you put your telescope? Newton was very, very worried about this. Where did he have his telescope? Well, in Cambridge. Where was the Greenwich telescope? Well, obviously it was in Greenwich, near the middle of London. But Newton realized that if you wanted to see things better, if you wanted to stop the image at the back end of your telescope wobbling about due to the heat and turbulence of the atmosphere, one way round was actually to move up a local mountain. Let's get up above the grossness of the lower atmosphere. Let's pass through the clouds and let's get to where the air is thin. And so if, for example, I came along and said, look, Ireland, here is 2,000 million euro, go and build a seriously big telescope. You would then have to sit down and think, right, where shall we put it? Shall we put it in County Offaly, where Birr Castle is, where the biggest telescope in the world was in the 19th century? Or shall we stonk off somewhere a bit better, say Hawaii or California or somewhere nice, a Chilean desert and so on? And so here you get the actual answer to the question, high up, the higher, the better. If you're 5 kilometers up, you've got 41% of the atmosphere underneath you. So that's good. Clear sky, fair enough. You don't want to go somewhere, I'm not going to be rude about Ireland, but it does rain a bit, does it not? I mean, you want to go somewhere, you know, like California, where it's seriously boring. It rains on 5 days in the year, and for the rest of the time it's clear. And you don't want humidity because you know that one of the greatest greenhouse gases is H2O, and the less of that you've got in the atmosphere above your telescope, the more of the infrared comes through, so that's a good scheme. You also know, if you're astronomers, that when it comes to the sky that you can see from a specific latitude on Earth, you are limited. So, for example, if you're standing on the North Pole, you can only see the North Celestial Hemisphere. And, of course, if you're on the South Pole, you can only see the South Celestial Hemisphere. If you're at the equator, you can see the whole lot, so that's quite useful. When it comes to a telescope, benign is important. Friendly government, a few spiders maybe, snakes, you don't like them. Well, it's this friendly government that's rather interesting. The Brits decided that they wanted a big southern hemisphere telescope. And so the South Africans said, oh, you can come down here and stick it with us, no problem. But of course, South Africa was in serious trouble at that time. The Chileans said, oh, bring it here. But that was a communist dictatorship. They said, no, we won't do that. And then the Aussies said, well, why don't you bring it to Australia? And of course, Aussies, they're nice people, so that's exactly where we put it. But when you go to that telescope, and I've used it happily, there are all these lovely, dangerous spiders all over the flipping place. And when you go to South Africa and use that telescope, the snakes aren't all that fun. And of course, you're building a telescope on top of a mountain, so if you're doing that, you've got to build the roads up there, you've got to get the water and the sewage up there. This costs you millions of quid, because your telescope's in the middle of nowhere. And so once you've decided which mountain you're going to build it on, you then get in touch with a few mates and say, do you fancy putting a telescope next door to ours and paying for the infrastructure? So you then find quite a few of them up there. And it's got to be accessible-ish, which really means that you need a small dark town about 40 kilometres away with a small airport near it, so that the light pollution is absolutely minimal. And when you go to a place where the light pollution is minimal, it is absolutely frightening. I mean, I live in Sheffield. Sheffield, the sky is orange. It never gets anything other than orange. And it's never black. And I've been in the sort of Botswana jungle where the sky is black. And people say, you can't see your hand in front of your face. You can't see your hand in front of your face. You can't see anything. It's so dark. It's terrifying. But there you go, where we are. Upstairs, well, of course, you build it upstairs, typically about 10 to 20 meters above the ground surface to get away from microturbulence. And you cover the ground with low shrub, usually some sort of desert-type shrub, because you don't want trees producing a lot of water vapor and so on. So you have this whole series of things that you need to do. Now, the first person who sussed this out was Charles Piazzi Smythe. This chap was Charlie Smith before he came a bit posh. Piazzi, his granddad was Giuseppe Piazzi, the gentleman who discovered the first asteroid in Palermo. Charles Piazzi Smythe really got things going. He took his new wife on his honeymoon to Tenerife with his telescopes. Would you believe it? That's what astronomers are like. And he schlepped up the mountain with his telescopes and did some seeing testing and realized that elevating your telescopes was really a very, very sensible idea. This is the telescope he took. This is a 3D image, so I apologize about this. This is the telescope he took to test the site. And these are the sailors that the Navy gave him to lug the telescope up the mountain. They don't look very pleased at having to lug that telescope all the way up the mountain, but that's exactly what happens. And so this is what astronomers do. You select a decent mountain, Kitt Peak, 2.5 kilometers up above sea level, and you build a telescope. And then you say to your friends, as I've said, would you like to build one? Would you like to build one? Before you know where you are, you've got 22 of the flipping things on top of your mountain there at Kitt Peak in Arizona. Superb observing site. Well, if you don't like going 2.5 kilometers up, you can go 4.2 kilometers up. And this is getting a bit high. You know, people can quite easily suffer from altitude sickness when they get up there, but here we are in Mauna Kea on Big Island in Hawaii, right in the middle of the Pacific. The airflow across this island is linear, very little turbulence. You've got nearly half the atmosphere underneath you. These are clouds, obviously, but they're not clouds above you, they're clouds below you, so you ignore them altogether. And you're on top of a volcano, but luckily this is an extinct volcano, so you don't worry about that. You know what Hawaii is like. The whole plate is moving, and so one island is being volcanic at the moment, but the further north you get, the deader they are. So you're on top of a volcano. And just look at it. Telescope, 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 telescopes all over the place. And the people who are living here don't live up here, they live down a bit because you can breathe a bit easier if you go down the hill a bit. Because in the olden days, we didn't bother about that. So when you go to Edinburgh, where was the telescope? Well, it was on Carlton Hill here, slap in the middle of Edinburgh. You went to Copenhagen. Where was the telescope built in Copenhagen? On top of this building, which, as you all know, because you've been to Copenhagen, is right in the middle of town. Unbelievable. You go to Paris, 5th arrondissement, the telescope owned by the Sorbonne. Where's that? Well, it's in the middle of the 5th arrondissement, here, with the whole of Paris all around it. What do you think the seeing is like with an instrument like this? Well, the short answer is the seeing is rubbish. It's an absolutely terrible place to be. So there you go. Now, in the history of telescopes, what I love is not just the successes. And I do think when you're teaching a science subject, you've got to, okay, we do tend to concentrate on successes a lot, but there were some absolute major drop-offs as we tried to advance. And this was one of them, and I love it. This instrument here, which is the Melbourne telescope, big telescope, 48-inch mirror at the back end here, built obviously in Melbourne. This mirror, I don't tell you, was made in Ireland and shipped out to Australia. Now the Aussies, bless, wanted a big telescope, but they were a bit on the mean side. And so they said, look, it doesn't rain much. We'll not bother building a dome. Big mistake. Any wind wobbled the top of this thing around. When it came to this mirror here, this was a metallic mirror, because those were the days when if you wanted to make a mirror, you made it out of metal, speculum. And the chemists used to sort of sit there wondering how to make a decent speculum mirror. And of course, typically the ingredients are 3 parts copper, 1 part tin, 1.5% arsenic, mix it all together, melt it up, nice mirror. Lovely mirror for a day. End of a week, bit tarnished. 3 months, ridiculously tarnished. So of course when this mirror got to Australia, it was nowhere near as good as it was when it left Ireland. So what did our Australian friend do? He got out the brasso. What did he do? He ruined the mirror. So he had to send it back to Ireland again. Well, putting it crudely, this telescope never worked. And so reflecting telescopes were put back engineeringly. For 30 to 40 years, people just stopped building reflectors and concentrated on building refractors instead. And I don't want to go all through the complicated details, but when it comes to a refractor, you've got a big lens here at the front end, through which light has to pass. And so the the lens glass has to be good, because the light has to go through it. So you don't want bits of straw in the glass, or bubbles in the glass, or that sort of thing. And of course, you've got a big convex lens. So if you've got a convex lens which is that big across, you imagine how thick it is at the center. And if you've got a convex lens which is that big across and is looking straight up, imagine how the shape changes if I change it from that orientation to that orientation. So you've got some big problems there with that sort of lens. And it's a lot easier to have a mirror, because with a mirror, all you've got is one surface reflecting the light instead of 2 surfaces with the light being transmitted between them. With a mirror, in essence, you can have any old glass to make it out of, because you're only figuring one surface. You don't have any old glass or metal to make it out of, but with a mirror also, instead of only being able to support it around the edges, you can also support it from the back, which is ridiculously helpful, especially nowadays with mirrors which you can computer control the rear surface of. Very, very exciting and so on. So all this starts to come in. In Ireland, you had this wonderful telescope at Birr, and this mirror here was 70 inches across. Biggest telescope in the world for 75 years. Do look at the Whirlpool galaxy outside. The greatest picture of that was produced using this telescope. Marvellous, marvellous instrument. And this was the lads making the mirror. And of course, this mirror would last as a shiny object for about 3 months. Then what did they do? They melted it down and made it again. So they had 2 or 3 of these mirrors, one in, one ready, one being repaired, and so on. Well, we've got one. I'm very embarrassed about this. I'm always very embarrassed about this. We've got one in the cellar of the Science Museum in London, and will we let you have it back? No. Tough. I'm sorry about that. There we go. When it comes to the advancement of astronomy, this chap was seriously important. Open any history book on astronomy, see if you find his name. It's not there. Liebig. What did he do? Chemistry lady at the back. This chap worked out how to put silver on glass. He simply worked out the chemical process of producing a silver film on a piece of plate glass. Putting it crudely, this man made a mirror. And he was a lovely chemist. He worked in his lab. He made a mirror. But he also had, very usefully, a mate. And the mate here is Steindl. Where's my technical expert? I'm sorry. I've pressed the wrong button. This gentleman here used the discovery of his friend, and he then started to manufacture glass mirrors which had silver surfaces. Now, glass, we all know, is much less dense than metal. So a big glass mirror weighs a lot less than a big metal mirror. This means that engineeringly, if I can support that size of metal mirror, when it comes to a glass mirror, I can support a bigger one and therefore easily make a bigger telescope. And so this is what then really started to happen. And we moved from these metal mirrored telescopes to glass mirrored telescopes. Here's a perfect example of the mirror of a big telescope. Glass, a glass honeycomb. It's not really glass, it's a Pyrex material which hardly expands as the temperature changes. All you have to do is to coat this front surface with silver. In the dome of every big telescope, you have a vacuum plant which can do this coating. It usually takes about 3 hours to do it. So as soon as the sun comes out, you can take the mirror out, stick it in the vacuum. 4 hours and a cup of coffee later, you've got a completely new silvered surface back in the telescope. You can work again the night after. Absolutely marvellous sort of process. But because the Melbourne telescope was so awful, you had these big refractors. This is Lick. If ever you have the chance to go and see this, it's at Mount Hamilton. And what you've got is a 38-inch lens at the top end. Because you want decent magnification, this lens has to have a, quote, reasonable focal length, which means that the focal length of this is about 40 foot. This means you need a dome, which is huge, and you, the observer, stand on the top of these stairs here, looking through the telescope. And if you're pointing at the sky, you're okay here. If you want to point near the horizon, telescope goes up, you switch your button and the floor goes up with you on it, and you can look where you like. Marvellous instrument. It's called the Lick, after a gentleman who bought some fields in California, and then the Americans kindly built San Francisco on top of the fields. So he sold the fields for a ridiculous amount of money, and as a memento of his life, he wanted to put a telescope in the middle of San Francisco, but luckily the astronomers said, no, that's a bit naughty. Let's stick it on top of Mount Hamilton close by, 1.5 kilometres up, and that's what you've got nowadays. Whoops, this is what it looks like today. Lovely, lovely thing. A great example of Victorian engineering, and this started working in 1898. Oops. This is the lens. Just look at it. What a cracker. This is Yerkes. As soon as California had got a big telescope, the mid-states wanted one too. And Yerkes was another chap, nothing at all to do with astronomy. Yerkes owned trams. In essence, he owned half the trams in the world. And when he died, he spent all his money on this telescope here. And this is in a lovely suburb miles north of Chicago. This again is a beautiful example of a telescope. This is the Crossley. And this is another telescope that is really historic, because when it comes to the history of telescopes, you also have to, in the back of your mind, the history of detectors. And when it comes to the history of detectors, there are certain dates that are important. And the first date is really about 1880. Before 1880, if you wanted to detect anything with a telescope, you looked through it. If you wanted to record what you see, you drew it. So all the astronomy students had lessons in art, because that was the way, for example, Ross represented his Whirlpool galaxy, Messier 51, by drawing it. In 1880, photography had become sensitive enough for people to be able to photograph stars through telescopes. So you needed telescopes which couldn't just have somebody peeking through them, but a telescope which could have a camera at the back. And this instrument was the first one that satisfied that condition. Here's the mirror and so on. And this then advanced until I was going to go through the other detectors. Let me see. The next detector, of course, is the charged couple device. And I mean, I can remember being grey at the moment when charged couple devices hadn't been invented. Then, of course, I can remember the time when our military friends very kindly said, we've invented this. We're moving on a bit. Would you like some of the old chips? And so the astronomers started using these. When we went to Australia to image Halley's Comet, we used one of the biggest, most sensitive CCDs we could get our little hands on, which, very thankfully, the American military had given us. And nowadays, well, half of your phones have got CCDs in and can take superb images that can go straight into computers and do all sorts of magic things. When it comes to telescopes, though, we have this history of telescopes increasing in size, becoming bigger and bigger and bigger light buckets, until, for example, you go past a few sort of milestones on the way. And one of the milestones was 100-inch, 2.5 meters. In 1917, this instrument, the Hooker telescope near Pasadena in the USA. Please don't ask me who Hooker was, because he was another rich American who just gave his money to help build this. This instrument came on first light in 1917. And what you've got here at the bottom end is your 2.5 meter mirror in a superb yoked English mounting, secondary at the top end here. And this instrument was big enough to firstly collect enough light from distant galaxies to enable people to get a spectrum of that light. Secondly, it was big enough to observe distant fuzzy things in such detail and with such magnification that you could tell that these were actual spirals. So 1917, this instrument came on board. After using it for 10 years, two little discoveries were made astronomically. One little discovery was that instead of the, quote, universe that we live in containing one galaxy, the Milky Way that we occupy, it actually contained round about 100,000 million galaxies. This is what I like about astronomers. When we make a mistake, we don't make a little mistake. We say, we went in and said, we went to do a lecture theatre like this and said, I'm ever so sorry. You know, yesterday I told you the number was 1. Well, it's not. It's actually 10 to the 11. And then, of course, the next discovery that this made was about, quote, this distribution of galaxies. As soon as somebody says, you know, I've discovered there are 10 to the 11 galaxies, you say, well, how are they moving? Now, of course, scientifically, there are two ways of things to move. One is that the whole lot spins round, so that you're equating gravitational force with centrifugal force and everything stays reasonably stable, and that's what's happening to our galaxy. The stars in our galaxy are going around the central nucleus, no problem. We looked at the other galaxies in the universe and thought, well, they probably are spinning round a great central nucleus. So if you look at a galaxy out there, you're expecting it to move like this as time progressed. Oh no. Using this Hooker telescope, you realize that these galaxies weren't moving around, they were moving away. Also, you discovered, shock horror, that the further away the galaxy was, the faster it was moving away. And then it doesn't take you long, I mean, half a coffee break to think, blimey, if these things are moving away now, faster and faster, if we go back in time, they must have been closer and closer and closer together until, whoops, if we go back, in this case, 10 to the 9 years, they worked out, all these galaxies would be in one lump in the middle. And then someone said, something must have gone bang to make them move out. And then you start getting this very peculiar breed of astronomer called a cosmologist, who sits there for hours worrying about the universe going bang and expanding and how will it all end and why did it go bang and what was there before it went bang and so on. So it's all down to this telescope here. And since this telescope, a telescope 2.5 meters across, again, let me stress that every 50 years we double the size of the telescope. So we are now sitting here around about 100 years after this thing started working. So we're expecting our telescopes today not to be 2.5 meters across, but to be 10 meters across. What have we discovered by doing that? Nothing. Nothing new, really. I mean, we've crossed the odd T and dotted the odd I, but we haven't discovered anything seriously fascinating using big telescopes. We've discovered there's a lot of missing stuff out there. And again, please don't ask me what this missing stuff is, because I haven't the foggiest idea. This is why I like astronomy. You're dealing with a subject that we are seriously ignorant about. And when I started being an astronomer 40-something years ago, we were ignorant then. And today, we're even more ignorant. We've got more things to worry about. You know, when I started off, there was no things like galactic inflation. God knows what that is. I mean, that's another complete mystery. But anyway, off we go. You've got a 2.5 meter telescope. You're never satisfied. Scientists should never be satisfied. You want a bigger one. And so you ring up Mr. Carnegie and say, look, how about slipping us a few pennies? Let's have a 5.2 meter Hale telescope. Here it is. Wonderful, wonderful instrument. And then, whoops, you just simply keep going, trying to build bigger and bigger things, and using engineering to do this. Look at the engineering of this, the skill in supporting that huge lump of glass and enabling it to focus on a small star in the sky. Absolutely wonderful. All this engineering, vitally important. Now, completely useless, because we have invented something else. Well, not we astronomers, but some kind engineer has invented the computer. So we can now go around and we can throw all these away. We can throw away the German mounts, the fork mounts, the pier mounts, the horseshoe mounts, and so on. And we can produce a very, very simple out-azimuth mount and use computers to control the movement. I just want to show you 3 quick graphs and then a few more pictures, and then I will stop for a question or two. This just underlines the way in which the diameter of the biggest mirror in the biggest telescope on the surface of Earth has changed as a function of date. And I've stopped at 2000 here, and as we're scientists, there's absolutely nothing wrong with us expecting this to keep going on up here through the roof. OWL is already on the drawing boards, and OWL stands for the outlandishly large telescope. I love it. And we're really working at it. This shows you the out-azimuth system. You have just 2 axes, one which is horizontal, one which is vertical. So the engineering becomes ridiculously more easy. And with those twin axes, with computer control, you can move the telescope exactly where you are. I'm just a bit, hold on a minute. I seem to have lost some pictures. Oh, they might come up somewhere else. This is Gemini. These are telescopes with mirrors 8 meters across. And this is a typical example of the sort of biggie that we can produce at the moment. And this thing here is yours for roundabout, bottom line, 100 million euro. This is about 10% the cost of a decent space mission. So if you don't fancy sending a spacecraft to Mars, you can build 10 of these. And lovely instrument. But you can also leap off into space. And I want to finish this lecture by just showing you how we have done that. And this is the Hubble, which has seriously revolutionized astronomy. All the pictures, and I mean all the pictures that you look at outside, have been produced by this beast. And in essence, all we've done is move up a bit. So instead of being on top of instead of being on top of a mountain down here, we've simply gone 600 kilometers up. And because we have superb computers and we can control things, we can allow this thing to pop round the Earth, as it does every 96 minutes, at a English unit here, speed of about 7,500 miles an hour. And you can simply point this thing at the darkness of space. There is no atmosphere. Everything works perfectly. Marvelous thing. And at the back end, you've got all these instruments, big mirror here, secondary mirror there, solar cells to power it, and you've got cameras and spectrometers and all sorts of gizmos at the back. And also, because it's only 600 kilometers up there, if something goes wrong, you can get the repair truck out and send it there. I mean, okay, it costs you a heck of a lot of money to hire the shuttle and your 7 astronauts and so on, but it can be done and really has proved how scientists have been able to advance. Very, very exciting. Here's some more detail about the Hubble. And I'm just going to finish off showing you a few of the things which are on the drawing board and coming along. These are the next big telescopes. You can see the size of the car. What we want to do is to build something which is not 8 or 10 meters across, but which is getting up to 40 to 100 meters across. This, needless to say, is the next step. We've got the 8 meters thing on the ground. It's a waste of time just increasing the diameter a bit. We've got to go double or so, and that's the plan. You can try and get the added resolution by having 2 telescopes. This large binocular telescope is already being built. Here it is. So you can now resolve as if you've got a single mirror which goes from there to there. Fantastic. And of course, instead of being stuck with a primary single cell of glass, engineeringly, people have got very, very clever so that they can build mirrors now by simply screwing together lots of bits. And when it comes to the next space telescope, this is it, due to launch in about 10 years' time, a seriously large mirror at the L2 Lagrangian point, a place where you can't visit and repair, but there you go, and that is the next step. Now, I'll just finish off by chatting for a minute. What have we been doing throughout the history of astronomy? We've been building bigger and bigger telescopes. We've been seeing fainter and fainter things. We have been seeing greater and greater detail. Why do we want to see fainter and fainter things? Well, there are 2 reasons, basically. If something is faint, it is either very small and close to, and me, being a person interested in comets and asteroids, want to see small comets and small asteroids, so I like that idea. But for our astronomers and cosmologists and galactic experts, if you build a bigger and bigger telescope, you're looking at something like a Milky Way spiral, which has a certain energy output. So if you double the size of the telescope, you increase the area of the mirror by a factor of 4, and you increase the distance at which you can see a spiral galaxy by a factor of 2. If if you increase that distance by a factor of 2, again, you're all scientists, you can see 8 times more. And you can see further out into space. And because light takes time to travel, you can see further back into time. And we all sit here today and we say with great certainty that the Big Bang took place 13,000 million years ago. You all know what the velocity of light is. This means that, quote, I hope there's no cosmologists in the audience, the edge of the universe is 13,000 million light years away. So I want to stand on Earth and I want to see what the edge looks like. I can't do it yet. But you give me a serious big telescope and I will be able to. So let's just keep at it, and in the next 100 years, who knows what we will discover. Thank you very much.
Okay. Many thanks to David for really kicking off, I think, today's presentations and talks. David has kindly agreed to answer maybe some questions when you're on, so we'll let you select questions. Any questions, David?
Just one question, right? As far as bang for buck is concerned, right? You had the James Webb and put up to space, and now you have the big owl telescope here. With interferometry and adaptive optics, how are we in relation to the cost of putting something big on Earth and getting the images that we would get from space, even though on different wavelengths?
You've put your really finger on a very interesting point here. In the visual, we're better off spending the pennies on Earth, because the visual comes through the atmosphere without any hassle. But as soon as you start wandering off, so if you want to go into the UV or to the infrared, getting away from our atmosphere is important, vitally important. And so this thing, the James Webb Space Telescope, is not going to be a visual instrument at all. It is simply going to concentrate, a bit like Spitzer, on the infrared, which can only be done properly from out there. And that's why we're so willing to spend so much money on this. Obviously, again, as physicists, you all know what Wien's law is. So if you're using the old visuals to see things, typically you're seeing objects with temperatures between, say, 3,000 Kelvin and 30,000 Kelvin. And if you turn around to me and say, just a minute, I want to see objects with temperatures between, say, 1,000 Kelvin and 200 Kelvin, I say to you, well, forget the visual. We've got to go to the infrared. And then you send to me, okay, forget the surface of the Earth. We've got to go up there to do it. And if you turn around and say, I want to see objects with temperatures that are 6 million Kelvin, you both forget the visual and the infrared. You go to the X-ray telescopes, which again have to be out there in space. Yeah.
Could I just ask a quick historical question about von Liebig? His managing to deposit silver on glass, would it by any chance be the aldehyde silver nitrate silver mirror test that we used to do back around?
I'm ever so sorry. You're talking
You're
talking to a man who, after the first year 6 at chemistry, decided I would never, ever open a chemistry book again.
You're in good company.
And
Fred Boyle did the same.
the reason I'm standing here is because I fell in love with physics and maths, and out of love with chemistry, so I do apologize. What the dear old lad did was put silver on a bit of glass, and that's the end of my complete knowledge on that subject.
Just thank you for the talk. I mean, particularly some of the visuals, the pictures of some of the telescopes were fantastic. I mean, there's toys for big boys in the RDS, but I mean, some of the toys you showed us up there would do it for me. And I get my transition year students to actually make a simple telescope on the Kepler design. So your pictures of the lick there, I haven't actually seen some of those. And the lens, you had a nice picture of the actual lens. Is there anywhere I could get hold of some of those?
Oh, I'm terribly sorry. When it comes to PowerPoint presentation, it's Google image all the way,
Nice. It was just fantastic.
and off you go.
Thanks.
But when it comes to a normal telescope, as I say, when it comes to the Earth that we live on, we now have round about 160 telescopes bigger than 3 meters in diameter, scattered around the surface of the Earth. Each 3-meter telescope and the bigger ones cost, typically, bottom line, round about €20,000 a night to keep going. So that's all you need. I mean, and don't forget, you can get with the CCDs a huge amount of data in one night. A typical proper research astronomer can get by with round about 6 to 10 nights on a telescope in a year. Now those are the observationalists. You've then got rooms full of theoreticians that all you need to do is to give them a pencil and a rubber, and that keeps them quite happy. And so when it comes to this number of 160 telescopes bigger than 3 meters, for each telescope that's lurking out there, you've got round about 10 to 20, quote, professional astronomers, people that WIT will employ to lecture on astronomy and allow to do research as well, working away. So this gives you an idea of what planet Earth is up to when it comes to astronomy and telescopes. And don't forget that I come from Yorkshire. All astronomy is completely airy-fairy. It does not, as they say in Yorkshire, affect the price of fish. And I am always grateful to the British and the European taxpayer for coughing up and, for example, giving me a job at Sheffield for 42 years, which I enjoyed hugely, just being an astronomer and teaching people to be astronomers and playing around with telescopes.
Sorry, just one there. To know, is there a proportion for, we'll say, the expansion of the universe and the stars and everything, and the development of telescopes now catching up to that expansion? In other words, would it be possible to predict, if things kept going the way they were, that in 100 years' time we'd be able to, we'd be after catching up to the rate of expansion? Or will the rate of expansion, in other words, will you never reach that goal that you were saying about being able to see?
There are complexities which, of course, I've not really underlined. I mean, as you know, the further away it is, the faster it's going, and therefore the greater the Doppler shift. And so if you have a star, take the sun, for example, that produces its maximum radiation at a wavelength of about 500 nanometers, you take the sun and stick it halfway out into the universe, this 500 nanometers has gone right out the visual into the infrared. It's been red-shifted so much that you can't just sit on Earth with a big telescope. You've got to go up there. And then if you keep expanding, you say, okay, well, let's go for hotter stars, which are emitting their maximum radiation in the ultraviolet. The red shift will move that into the visual, we're okay, but as you get closer to the edge of the universe, it's moved it out the visual again towards the infrared. And so we're getting to this impasse, or certainly in 100 years' time, we will be in a bit of trouble. But there again, in 100 years' time, we'll have a room full of people like this living on the moon, with telescopes on the moon, where it's dark for 14 days and then light for 14 days. And we won't bother about popping up into orbits. We'll just be sitting on the moon using those, maybe. Sorry.
Right, a mirror has to be so big. A CCD can be so big. I know they've made them up to, 600 mil across now, and they're thinking of sticking one of those into space. But will the day come that we won't be using mirrors at all and just use charge-coupled devices and chips and whatever as collectors?
Well, I don't think so, no, because I mean, the number of charged coupled devices that you're using actually to take pictures with in space are fairly limited. I mean, you go outside and you can see all those lovely pictures, and these lovely pictures are just that, lovely pictures, but they don't tell you much. And so most astronomers will be using spectrometry. And there, of course, you're putting your CCD at the back of a spectrometer, and all the spectrometer has got at the front end is a little slit. And what you're trying to do then is simply push energy into that slit. And if you've got a very distant object which is very faint, you need a huge light bucket to collect up that energy and focus it on that slit. And that is the basis of modern telescopes. And so when it comes to using a telescope in space, you would find that 99% of the time that telescope is taking spectra. And then 1% of the time someone says, let's take a nice picture. And they're superb pictures, obviously, but that's the way it goes, yeah.
We once again thank David for a fantastic talk.